Thursday, February 22nd. I'm going to go over the slideshow, Atmosphere Basics. This refers to back in your textbook, Module 8, Lesson 1. And we've got some notes to take during this, and then I will assign the Smart Book assignment. So let me go over and go to a Schoology. Schoology, you have just finished the quiz. You can see the Smart Book assignment here. And I will put this notes assignment in there. These are the focused notes. This will be, I will put it in as a Google Doc, and you can just type in. And to do this, I will give you the topic objective, and I'll give you the essential question. You can type those in. Feel free to type your name in, but I will have that as part of the Google assignment. And then I will go in order. Feel free to stop the video as you need to get the information down. And I also have a link to the slideshow on Schoology if you want to follow along with that. Okay, so let's go to the slideshow. It's called Atmosphere Basics. And we start off, this is Module 8, Lesson 1 refers to the textbook, right? We're doing Inspire Earth Science, and you can access that textbook either through the assignments I put on Schoology, or you can access it through Rapid Identity. It's a green tile that says Inspire Science. Okay. We start off with focus notes. These are Cornell-style focus notes that you're doing. And the topic today is Earth's atmosphere. So go ahead and write that in on your Cornell notes sheet or type it in. And the essential question is, what is the structure and composition of the atmosphere? Pause the video if you need to write it down, and we'll move on to the next slide. We start off by talking about just what is air. So air is defined as a mixture of gases, particles, and water droplets. It is a mixture. It is colorless, invisible, and it's what makes up Earth's atmosphere. So what is Earth's atmosphere? We define the atmosphere as the envelope of gases that surrounds the Earth. Okay. Now, Earth has some atmospheric gases that remain over long periods of time at the same percentage. Okay. And we call those permanent atmospheric gases. For example, nitrogen, every breath you breathe in, if you breathe in a breath, 78% of every breath you take is nitrogen, and about 21% is oxygen. Okay. The remaining 1% or so is argon, and then there's what do we call trace gases. Trace means a very small amount. Okay, there's a very small amount of those. So these are the permanent gases in our atmosphere. If they're not permanent, we call them variable because they vary in amount. They can change over time. And some variable gases are shown in this table. Water vapor, carbon dioxide, ozone, and methane is also shown. Let's start with water vapor. Water vapor is invisible. Now, is steam water vapor when you boil water? Well, steam, the stuff that you see is actually water droplets, liquid water. But steam, before you can see it, before it condenses back into liquid water, is water vapor. But what we mostly think of as water vapor is the stuff in the room right now. There's a certain percent of our air that is invisible water vapor. Comes from breathing out. It comes just because it's part of the air outside. Evaporation puts it into the atmosphere and so on. As you probably know, water vapor can vary over time, right? In the winter, you use more lotion on your hands because the air is very dry. You might have more static electricity or you give your friend a shock in the winter. Whereas in the summer, it can be very humid. Right? We can get a lot of rain. We can have, in Minnesota, we have a lot of fields of corn and other plants that through transpiration give off water vapor, and we have very humid August, late in the summer. So water vapor in the atmosphere can range from 4%, which is very humid, down to nearly 0%. So you can imagine a desert would be nearly zero, and possibly a tropical rainforest might be around 4%. The next variable is carbon dioxide. We've heard this in the news quite a bit. Carbon dioxide currently makes up about 0.038%, so very small amount of our atmosphere. During the past 150 years, it has increased. It used to be about 0.028%. So over the past 150 years, the level of carbon dioxide in the atmosphere has gone up. And so that's why we call it variable, although the percent is over short periods of time remains relatively constant. It is going up every year. We'll take a look at that in class. It's a pretty interesting graph to look at because it varies according to what time of year. There are certain times of year when there's more carbon dioxide in the air, and there's certain times of year that there's less carbon dioxide in the air, as measured in the northern hemisphere especially. Now, carbon dioxide is also cycled in the atmosphere, right? As you know, you breathe out carbon dioxide and you take in oxygen, and plants take in, as part of photosynthesis, take in carbon dioxide and give off oxygen. And so there's other things in which, so I'm referring to animal respiration and plant respiration. Plant respiration, yes, plants also respire. Plants give off carbon dioxide, but they also take in carbon dioxide through photosynthesis. And then you can see over here fossil fuel combustion, the burning of fossil fuels by factories and cars puts carbon dioxide into the atmosphere. So this is what we call the carbon cycle that we'll certainly take a closer look at some other time. I don't know if you've heard of ozone. So ozone is bad at the Earth's surface. Ozone is what's given off by cars and factories, and it produces something called smog, and it can be bad to breathe in. But if you go up higher in the atmosphere, called in a layer called the stratosphere, we'll get to that in a little bit. Stratospheric ozone is good. Not just good, it's necessary. It's required for life on Earth. And why is it required? Because stratospheric ozone does something very beneficial to us. And it's not that it cares about us, but we benefit from it. It blocks UVC and part of UVB radiation. UV is ultraviolet. Okay, so this is the stuff that causes cancer. This can cause skin cancer if you don't use sunblock. And fortunately, the ozone actually blocks the worst of the ultraviolet radiation coming to Earth. So, ozone is a molecule. It's composed of 3 oxygen atoms. We call that, the formula is O3, we say. And it's located in what's called an ozone layer. It's not a thin layer. It takes up quite a bit. It's not like a layer like you see put together real close to each other. It's spread out between 20 and 50 kilometers above Earth's surface, and it protects us from ozone. It actually absorbs it. We'll get to that more in a little bit. One thing, though, there's a chemical that we call CFCs. It stands for chloro, means it has chlorine, fluoro, which means it has fluorine, carbons, which means it has carbon. Chlorofluorocarbons are used as propellants. Used to be used in aerosol cans, isn't so much anymore, but it's used in fire extinguishers and other things like that. The thing is, it goes up in the atmosphere and reacts with ozone. And it's not just a little bit of CFCs will react with hundreds of molecules. It'll just keep going on with a reaction that breaks the ozone apart. You may have heard of a hole in the ozone layer. This is something that was identified way back in the 1960s or 70s, and legislation was done to ban the use of CFCs in certain products, and we've really decreased the use of them. And now the ozone layer has been closing, getting better. There are still holes, and we'll talk about that another time, but it's something that shows that humans can make a change to protect themselves. by saving the ozone layer, and it worked. Atmospheric particles, these are particles in the atmosphere like ash from fires or volcanoes, dust, salt, ice, all these things. We call those aerosols. That's kind of a collective term. And just think they can actually block sunlight, right? They can actually cause the planet to cool. A volcanic eruption in 1991 in the Philippines called Mount Pinatubo erupted and put so much ash in the atmosphere that the entire Earth cooled down for like a year, cooled down by like a degree, but which is a lot. So atmospheric particles can block some of the sunlight. All right, layers of the atmosphere. So why it doesn't look like there's layers, right? Look up in the sky. I don't see any layers. It's actually according mainly to it's what's happening there, but it's also the temperature. So they differ according to temperature. Look at this red line. It shows that close to Earth, the temperature gets colder as you go up. That's temperature decreasing with altitude. And then it kind of goes straight up and then it increases. It gets warmer, then it stops and starts to decrease again and then increase again, right? And so scientists have decided that this is what we're going to refer to as different layers. So let's look at each one of these. The first one is called the troposphere. The troposphere is the layer we live in. It's the layer closest to the Earth's surface. This is where weather occurs. It contains most of the mass of the atmosphere. And as you go up in the troposphere, it gets colder. Well, you know that, right? You look at a mountain, you see snow on top of the mountain. You're in Hawaii, you're surfing on the beach, you go up to the Mauna Kea, and there's snow up there. Yes, it gets colder the higher you go up. There's fewer particles, there's less air to hold the heat and so on. All right, the top of the troposphere is called the tropopause. It's where the temperature stops decreasing. And so then we start moving into the next layer. The next layer up is called the stratosphere. It's above the tropopause. This is where the ozone layer is. Temperature in the stratosphere increases with altitude. Well, why? Why is it warming up? Because of the ozone. The ozone layer is absorbing that ultraviolet radiation, and that is causing the air in the stratosphere to heat up as you go higher and higher up. 99% of the atmosphere is below the top portion of the stratosphere called the stratopause. 99% of our atmosphere is below that. But there's still more layers. The next layer up above the stratosphere, above the layer, the boundary that we call the stratopause, is the mesosphere. Meso means middle. The mesosphere is the next layer, and that's where temperature starts to decrease again with altitude. And it can actually get quite cold to minus 60 degrees Celsius when you finally get to the top, called the mesopause. The uppermost boundary is called the mesopause. Okay. And the next one, thermosphere. Thermo means heat. So thermosphere, becomes the hottest layer, which is weird because it's so far up. And another weird thing, if you were at the thermosphere and you stuck your hand out the window, it wouldn't feel hot, even though it is. Why? Well, because there's not very many molecules up there. Heat is a measure of the kinetic energy, the speed of molecules. And that layer is absorbing so much radiation from space that it's heating up. It gets really, really hot, 2,000 degrees Celsius. But if you stuck your hand out of the window, it would feel really cold because the particles are so far apart that you're not feeling them colliding with your hand. The air is so thin up there. There's a layer called the ionosphere. Ions are charged particles, and that's part of this layer. The outermost layer is called the exosphere. Exo means outermost. The exoskeleton of a bug is the outer layer of the bug. All right, the exoskeleton. The exosphere is the outermost layer. There's no clear upper boundary. It just dissipates more and more and more and more. This is where satellites are and so on. This is thought of as the transition between Earth's atmosphere and outer space. The next section talks about energy transfer. So let's talk about what energy is. we get pretty much all of our energy from one thing, right? That big glowing ball in the sky we call the sun. And so, because of the sun, we have energy on our planet. Sure, there's a little bit of energy inside the earth, the geothermal and whatever, but for the most part, we're talking about the sun. So, understand a couple of things. All matter is made of particles, and those are all in motion. Unless it's at the temperature we call absolute zero, there's molecules of everything are moving. If they're solids, they're vibrating. If they're liquids, they're moving around. If they're air, they're moving around farther apart and faster. And so we call that kinetic energy. Kinetic means moving, energy of motion. The total kinetic energy of an object is called thermal energy, and you can measure that. Those particles are running into the thermometer when you put a thermometer in a liquid. And as it runs into the bulb of the thermometer, that causes the bulb of the thermometer to gain energy, and that heats up and expands and moves up in the column of the thermometer, and it registers as being hot. So heat is the transfer of thermal energy from a region of high temperature to a region of low temperature. That's the way heat travels. Radiation. Radiation is another form of heat transfer, or is a form of heat transfer, the first one. And this is in the form of waves. This is how we get heat from the sun. The sun's energy travels through space in the form of electromagnetic radiation and goes through our atmosphere and then hits the Earth's surface. Now, when it hits either clouds, it can be absorbed by the atmosphere, it can be reflected by clouds, all these things can happen. It can be absorbed by the Earth's surface, and that causes the Earth's surface to warm up. Oh, now the energy changes. Where it was electromagnetic radiation in a short wavelength, now it becomes a longer wavelength, something we call infrared or heat. Now it can be trapped by our atmosphere. That's the greenhouse effect. So solar radiation is absorbed or reflected by Earth's atmosphere and surface. And then as it's absorbed, it turns into ultraviolet radiation. Infrared. So this talks about absorption and reflection. Do you know the difference between those terms? Absorption means to absorb it, right? Collect it. Radiation from the sun passes through the atmosphere, strikes the Earth's surface where some of it is absorbed. You can see on this diagram, 100% of solar energy, 6 plus 20 plus 4% are reflected. That's called the albedo. 30% of the sunlight hitting the Earth is reflected back into space. So the rest of the 70% is all this stuff over here. Now, the rate of absorption, right? Land heats up faster than water. Water has what's called a high heat of vaporization, a high latent heat. And what that means is a swimming pool, right? It could be 70 degrees next week. You're probably not going to go jump in a lake, right? The land might feel hot. If you go barefoot on a paved surface, it might be hot. But the water isn't, because it takes a long time for water to heat up. The next type of heat transfer is called conduction. Conduction means heat transfer when something's in contact with something else. Okay. So, example here, if you look at the diagram, the ground heats the air, all right, because the air is touching the ground. The ground is heating the air molecules, causing them to rise. And the last type of heat transfer, we had radiation and conduction. The third type is convection. We've learned convection in the past, if you had me first semester especially. Convection, right, that's what's thought to aid in the motion of Earth's lithospheric plates. Well, on land, it can cause, let's say if you're next to an ocean and during the day you get a breeze coming in from the ocean. Well, why is that? That's called a sea breeze. And what happens is, over the land, the beach, right, it's hot, and the air rises because it's less dense. Well, as the air rises, it moves over the water. As it goes up in the air is cooler up there, and it cools off and sinks. And then the cool air from the ocean then moves in to replace the rising warm air. We call this a convection current. And finally, we learned a little bit so far about the greenhouse effect. The greenhouse effect is how our atmosphere retains heat. If we didn't have it, there wouldn't be any life on this planet. The moon does not have a greenhouse effect. All right, there's a 400-degree difference between the lighted part of the moon and the dark part. During night, because we have a greenhouse effect, because we have an atmosphere, it doesn't get to 300 below zero at night. So, what our atmosphere does is it holds on to it, traps the heat, and that's a good thing to a point. So, the trapping of heat by our atmosphere, like a big cozy blanket, is called the greenhouse effect. All right, so your assignment is to do the SmartBook Atmospheric Basics. You can find that on Schoology. If I go ahead and get out of this and go back to Schoology, you can see right here, SmartBook 8.1. I have this due on Friday the 23rd, so you're going to work on this today and hopefully tomorrow and get it done. And then we'll move on from there. So I might have to change the virtual investigation. We might push that back another day. We might do that next week, okay? So good luck. Hopefully you got your notes taken, and next is to do the SmartBook. All right, thanks.